call him and ask him to come here.
Him? Oh, how much? Sit. You can sit right here. Oh,
so all of you here for ECE 210, I suppose. If you're not from ECE 210, you might have come to the wrong class. What is this? Okay, my name is Uiuc. My name and then my office is 379EL, my email. You can buy this. And then my phone number is 3337309. Aditya, are you the TA for this section or is that assigned that way?
No, so we have I think 6 TAs, and it's not section wise.
It's not section wise, okay. Aditya is one of the TAs for this course. There are 6 TAs. And you can find that TA names from the website. Aditya is this name.
So I'll be their head lab TA.
You're the head lab TA?
Yeah.
Okay. And his coding is 378C. Okay. And we meet Monday, Tuesday, Wednesday, and Friday at 1 p.m. Okay, those are the lecture hours. And homework is due at 6 p.m. every Wednesday, I was told. Okay, I'm teaching the course for the first time. So it's due 6 p.m. every Wednesday. Absolutely no late homework, I was told that. Okay, so if you turn in your homework late, it doesn't count. That's what I was told by the course instructor. So make sure that you turn in your homework early and never late. Otherwise, everything you've done is useless. The textbook for this course is Analog Signal Systems. So this is the textbook used, and I'm sure you can get a copy of this in the bookstore. Analog Signal System with a very nice picture out front. Looks like that of the Grand Canyon or something. And Orhan Kudeki is the associate head of the department, and David Munson was with the University of Illinois, but now he's the Dean of Engineering at U of Michigan. He's not here anymore, but Orhan Kudeki is still here. You can bother Orhan Kudeki if you have any questions on the book, or just ask one of us. Okay, but if you don't like the book, let him know. You will like it. Okay. So this is a course about analog signals, and you may very well know that there are two kinds of signals in this world now. One is analog signal, The other one is actually digital signal, and most of us use digital signals now for some good reason. But this is a course about analog signals. How many of you do not know what an analog signal is? I guess all of you know what an analog signal is, right? Let me just give you a signals are functions of time. An analog signal might look something like this and so on. Okay? And then it could be a signal coming from outer space, it could be a signal coming from your loudspeaker, it could be something coming from your voice box. That signal will look something like that. Okay? But digital signal, on the other hand, looks something quite different. Instead of plotting it as a function of time, you might take the value here and plot the value here, the value here, the value here, the value here, and so on. And you get a picture of what I mean. Okay? You only sample the signal at every given interval. There's one very important difference of a digital signal. Okay, there's another very important difference of a digital signal, which is that these values are given a number. Okay, these values may be recorded on your magnetic tape. Like very old time, we have this VHS and VCR. Do you all still know what those are? Okay, your father or your parents might know. Okay, we recorded TV images on tapes. And the amplitude of the pixel on the TV is recorded as a magnetization on the tape. Okay, it's recorded as how strong the signal is depends on how much magnetic the magnetite is being polarized on the tape. Okay, so over time that signal decays. And if you have some very old tape from your father's time or your mother's time, you try to play them now, they don't play well because those tapes lose magnetization. Okay, so this information that are stored as analog signal in the tape are very dangerous. They get lost. So what engineers have done is to record this as a number. Okay, that's one important thing. Another important thing is that that number is digitized. And all of you know how to digitize numbers, I suppose. Like 1, 2, 3. This is how we learn how to count in the beginning. But for computer scientists, this is 0, this is 0, 1, this is 1, 0, this is what? 1, 1, this is 1, 0, 0, right? All of you know how to do this. So when you convert numbers into ones and zeros, they can be easily recorded. They can be easily recorded again on the tape or on some other devices like your hard drive memory, and they're recorded as zeros and ones. Of course, they don't look that nice though on the tape and on your hard drive. You will see something like this, and they might over time also become worse and worse and get washed out. Okay? But the good thing about digital signals is that they are error correcting codes. That you can actually look at this, and if one of the bits get washed out, this is called a bit. Okay, and if one of the bits get washed out and it doesn't satisfy certain rules of recording, that error get corrected so that it satisfies certain parity. So digital signals can be recorded much more securely, is one thing, with a lot less error, and can be lasting for hundreds of years if your DVD or your CD does not break down. Okay, of course it will break down over the years, but if they're not broken down, you can read the same thing again, maybe hopefully 20, 30 years from now on, or when you grow old. Okay, because when I grow old and I go back and read my old tapes, they cannot be read. It is quite bizarre. Okay, so there are pros and cons of digital signal, it means that one number here needs a lot of bits to record. But one number here just needs one value to record, which means that you need a lot more signal. You need a lot of signals to record this, okay? Whereas you need very little information to record this. So the pros of the digital signal is that it can last forever, just like diamonds. Diamonds are sometimes thought to be forever, but analog signals, when recorded, are not forever, okay? And another thing about sending signals over space. How do you send signals over space? Okay, you have to have the concept of a carrier. So if I want to send this signal over space, what we do actually is not to send this signal directly. Okay, we actually modulate a carrier. A carrier is just a very high frequency wave. This could be kilohertz range. Okay, it could be your voice signal, which is usually below 2000 hertz. Unless you have very special hearing ability, you cannot hear anything above 2000 hertz. Or if you are a special kind of animals, you can hear very low frequencies. Or if you're a very special kind of animals, you can hear very high frequencies. But our hearing range is very narrow. And in order to send this kind of voice signal over, you can use RF signal, which stands for radio frequency, in the order of megahertz, or maybe 100 to 1,000 kilohertz. Okay, these signals are very high. So what you do is actually to modulate the amplitude of this signal. So instead of sending the signals directly, you send them over a carrier. Okay, so the radio frequency that you use to carry that signal is called a carrier. It can be in the order of hundreds of kilohertz or megahertz. And then you modulate and demodulate this thing to get back the signal. I won't go through that. You do the same thing with the digital signal. You convert each of this signal here into something over here like this. And again, you will send it over using a carrier in terms of tone bursts. Ones and zeros, okay? So you would make something like this, but amplitude modulation, and then send them over a carrier. You can see that you need a lot larger bandwidth to send a digital signal compared to an analog signal. But we have the technology to do that. We have technologies going up to tens of gigahertz, hundreds of gigahertz. So we have lots of bandwidth to carry signals in this world right now. So digital signals will be carried in this manner. These are called amplitude modulation. And there are other ways of sending signals overseas, like FM, frequency modulation. Instead of changing the amplitude, we change the frequency of the carrier to carry the signal. I won't go through all those details. That's why recently, just in Urbana-Champaign, I believe it was about 5 years ago, we switched from an analog TV system to a digital TV system. And all of you who are here, maybe you are too young to be here then, you have to go to the shop to buy a new TV, which is a digital TV, or you buy a converter that converts digital signals that are being sent over the air now back into analog so that your whole analog TV can be used. Okay? So the book actually gives a diagram of how your cell phone works. Let me just go through that diagram very briefly. So you have a pressure wave when you're speaking to your cell phone, and that pressure wave gets picked up by a mic. The mic takes this signal, which is an analog signal because it follows the vibration of the diaphragm on the mic, and then it has to be digitized. So it has to have an A to B converter, and then it will have a computer or central processor to decide on what kind of signals to get rid of. Maybe there are lots of noise in that digitized signals. You do something to that. And then you have a D to A converter, which is digital to analog, and then you put that on an antenna. This is an antenna. And then you send them out as electromagnetic waves or microwaves. Okay, this is how your cell phone works in the transmit mode. You pick up the voice signal, this is your mic, and then finally it gets converted into an antenna, into an electromagnetic signal. And on the other side, as a receiver, your cell phone can also work as a receiver. You have an antenna picking up an electromagnetic signal, and then it goes through an A to D converter. Because this comes in as an analog signal, it has to be digitized. Once it's digitized, there are lots of things you can play with it. You can do error correction, you can change the quality of the voice, and all kinds of things. You do that with a computer, and then a central processing unit, and then do the digital to analog conversion, and then put that to a loudspeaker. And then this again creates some pressure wave. Okay, this is out. And this is how the cell phone works in block diagram. Okay? And there are lots of analog signals over here before you get the digital signal. So we will talk mainly about the analog part of the signal, which is also very important. Before digital signals came about, all the technologies that we have had in the past were analog. Digital technology is a very recent technology. So, analog signals are dealt with using circuit theory, using resistors, transistors, capacitors, and inductors, and all that kind of things. So we have to learn circuit theory in this course in order to learn how to manipulate analog signals. So we'll talk a little bit about that, about what circuit theory is. So this was like chapter 0 of the textbook. Okay, this is like chapter 0. So we go to chapter 1 of the textbook. In chapter 1, we will have to talk about currents, voltage, and power. And I suppose that most of you know what these things are. The current on the resistors, current on the inductor, current on the capacitor. And that if you have a resistor, you have a capacitor, you have an inductor. Then if you put them through a voltage source, current will start to flow. You will have a current through the resistor that we call IR, and then you will call R, L, and C, and then you will have different kinds of current through this kind of thing. So let's talk about what a voltage is. I'm sure that you have learned about voltages many times before. And you have learned about voltages in your Physics 212, maybe even EC 110. So we are revisiting that concept on voltage again. What is a voltage? Voltage is actually a potential difference. The kind of potential energy you can create in this world. And that energy can do work for you. And there are other kinds of examples of potential energy. But let me give you an example. Gravitational field. It's the kind of potential energy. You can think of the gravitational field as being something that always points downwards. And if you have a mass, this gravitational force will act on the mass and force it to go downward. That is what a gravitational field does. And you can also think of the gravitational field as being having created different potential energies at different levels. If the mass is over here, you have high potential energy. If the mass is down here, you have low potential energy. So you can use this potential energy difference to do work for you. For instance, if I have a slope, if I put a mass down here, I will know that it will roll down the slope because of the gravitational force that pulls it down. The gravitational field produces a kind of potential energy for this particle as it is put in a high place. Okay? You can have potential energy to do work for you. For instance, in a waterfall, in a dam. Okay, you dam out water, and then the water can flow down, and it can be used to drive turbines. And the turbines can be run to create electricity. Okay, that's another use of potential energy. Another way you can think of potential energy doing work for you is to have a kind of a machine where you have platforms at different levels. Okay, you have a ball, it will roll and it will drop down. And then it will drop down because it goes from high potential energy region to a low potential energy region. And then you can have another machine that takes this thing up and then drop it in another platform. Okay, you can have this thing keep going and going, but this one needs work at this part. Because you have to raise a ball from a low potential energy region to a high potential energy region and drop it at some high potential energy region and let it do work for you. Okay, this is gravitational field. But in electrical engineering, there's another kind of field that can do work for you, which is the electric field. The electric field can do work for us just like gravitational field can do work in other mechanical systems. Electric field has the power of being able to push a charge, a positive charge along. Say if you have an electric field, very much like the gravitational field that I drew over here, and if you have a positive charge, the positive charge will push in that direction. Okay? And if you have a negative charge, of course, it will be pushed in the opposite direction. And hence you can use this electric field to drive currents around a circuit. For instance, if I have a voltage source is nothing but something that can produce electric field out of it. If I can connect a piece of wire to this thing and then maybe put a resistor here, and this electric field can push the electrons around in the circle so that you can create current flow. Current flow is powerful because it can be used to do work. Like if this resistor is a light bulb, it can produce light. Okay? So a very simple example of the use of potential energy is the electric field created by a simple voltage source. The voltage source created a high potential energy region and a low potential energy region, and that the electron has to move, just like this moves over here from high potential energy to low potential energy. Okay? And then as it moves across this resistor, there will be a voltage drop. Because the electron loses potential energy as it goes from there to here. Here will be plus V, and here is 0 V. Okay? So it goes from a high potential energy region to a low potential energy region. Just like what happens here. As this ball drops, or this thing drops down, and as this thing drops down. Okay, that is the concept of a voltage and a voltage source. It essentially is a source that can create a difference in potential energy. Okay. Are there any questions so far regarding what a voltage source is? A voltage source is something that can produce an electric field, and the electric field produces a potential energy difference in your circuit. And that potential energy difference can be used to do work for you, like making your cell phone work and that kind of thing. Okay. Voltage is also defined somewhat differently. In the book, it's defined as the change in the stored energy, the power, with respect to the Q. Okay, because in your freshman physics, you probably learned that Q times V is equal to W, the energy stored in a charge. If a charge is placed in a potential energy of V, the charge actually has that amount of energy. Okay, from this relationship, you can deduce that voltage is also determined or defined as the limiting cause of the change in the energy stored over the change in the charge in the system as the charge in the system goes to 0. Okay, there's another way to define what the voltage is. And as a result, it can be written in terms of joules per coulomb, or just volts. And volts is, of course, named after the first person who invented the cell, the battery. Okay, I think his name was Potel. He invented the first chemical cell that we still use up to these days. Of course, the technology will be different. He was able to invent a kind of chemical cell that create a potential difference between the two polarity of the battery. And it was because of that that we had telegraphy. And because of him, we can actually make batteries that have positive voltage and negative voltage. And then if you can have a line, okay, you can send signals down this kind of thing. That was in the 1800s, early 1800s, that he was already able to do that. And that was the time when telegraphy was invented. Okay, just because of this kind of very simple invention. Are there any questions so far? And then current I is actually defined to be dq dt. Okay, the rate of change of charge in any system will give rise to a current flow. And you can think of this as limit of delta Q over delta T as delta T tends to 0. Okay, so it's the rate of change of charges in the system. Actually, charge has a very strange history. Electron was not identified until 1897, but people were manipulating electricity in the early 1800s. They were playing around with telegraphy in about 1826, 1830. They were able to make electrical machinery about 1830. But electron was not found, right, identified as a particle until 1897 by J.J. Thomson. So in the beginning, when people were manipulating electricity, they thought electricity was carried by charges that had a positive sign. Okay, they were positive charges moving around. But later, only did they discover that it was not positive charges that were moving around. It was actually electrons that were moving around. So when you apply an electric field, it was actually electrons zipping in the opposite direction of the current. The charges are thought to be moving in the positive direction. Electrons are moving in the opposite direction. But that was much later. Electricity and magnetism was already a well-established field. People didn't want to change their minds. Just like we don't want to change from Fahrenheit to centigrade in this country. We don't want to change from feet to meters, right? So people kept saying that electricity are due to positive charges. And when they apply the voltage, they flow in that direction. As if positive charges are flowing. But that is not the real thing. Okay? So currents are due to negative charges, but people thought that they was due to positive charges. Okay? So just keep this in mind as an electrical engineer. There's some tradition that you have inherited, and you just have to live with that tradition. Okay? So currents is in terms of charge, so it's in terms of coulombs per second. And this is, of course, those are amperes. Okay? And then you have the concept of power. Power is actually described to be V times I. It's the work done by the electricity as it moves along. Okay, as it moves along, what kind of work can it do? It turns out that power is defined by I times V. And if you look at the dimension, this is in terms of energy per unit charge. Okay, the energy done per unit charge, multiplied by the current, which is charge per unit time. So if you look at this and multiply this up, it's dW dq, dq dt, kind of thing, and then it finally becomes dW dt. So this is energy per unit time, and this has a dimension of power. Okay, so this is in terms of joules per second. and hence this is known as watts. Okay, all these names are very famous scientists. Bose is, of course, the guy who invented the voltage cell. Ampere's, what was he famous for? I think he was famous for telegraphy. He owned a telegraphy company early in the 1800s. What is Watts famous for? The steam engine, right? It was a Scottish man who invented the steam engine. Okay, maybe other people invented before he does, but we all think of him as being the inventor of the steam engine, and hence there's something to do with power. So everything that's something to do with power is named after Watts. Are there any questions so far? This might be just revision for you at this point, and let's talk about voltage drop and voltage rise. Okay. So, as we say, as the current moves through a device like a resistor, there's a voltage drop across it. This cell, this voltage cell, creates a high potential, and as the current falls from this high potential to a low potential, there is a voltage drop. So we usually indicate things like this way. You put the plus, we put the minus here, we put the VB. VB here means that the voltage here is higher than here. But if we say VB is minus 4 volts, it means the opposite. Because we say that even though this is higher than this, but it's minus 4 volts higher than this, it actually means that this part is lower than this. Okay, so when you have this kind of notation, be careful. And then we might have something like this. And then to make these two the same, we would say VB is 4 volts here. Okay, because we change the plus and minus sign around. This is one thing that we have to learn about voltage drops. Okay. And then in a circuit, you will have branches and loops and nodes. Okay, and I just want you to know what those are. These are elements of a circuit. Okay, it can be a voltage source, it can be a resistor, it can be an inductor, it can be a capacitor, but I'm not labeling them right now. But these are known as nodes, okay? Things or places where two pieces of wire meet, those are known as nodes. There are two ways you can stipulate a voltage in a circuit. One is to stipulate a voltage drop across an element like what I've done there. Another way is to give a potential to the node and say maybe the voltage here is 4 volts. And if you ground this system over here, connect to the ground, you see the voltage here is 0 volt. And then you will give a voltage here, maybe voltage here is 2 volts. Okay? Then by looking at this diagram, and if I ask you to figure out what the voltage drop is across C, what would you say? The potential difference. It will be 2 volts, right? In this direction, it will be minus 2 volts in that direction. Voltage drop also has directions, depending on how you stipulate it. And then if I ask you for the voltage drop across B, it will be 2 volts in this direction minus 2 volts in the other direction. Okay? Some of the things that you have to be careful about. And of course, you have currents. And currents goes in this direction of this arrow. You see the current is flowing 2 amperes in this direction, but minus 2 amperes in that direction. If this is the direction you have stipulated. Another thing you have to notice is that voltage is relative. Okay, voltage is always relative. I can make this to be my 0 voltage point. I can also make this to be my 0 voltage point. And for the same circuit, I can redraw it and connect this place to ground instead. And then in order for the circuit to be the same as the first one I've drawn, okay, so this point must be 0 volt now. What volt should I give to this node over here? in order for it to be the same as the previous diagram I've drawn. Yes? Negative 2 volts. Okay, so that this is 2 volts higher than that. And what potential should I assign to that point over there? Plus 2 volts, right? And then this diagram will be the same as that diagram, and the same kind of current would flow on the 2 diagrams. The same kind of power would be dissipated in each of these elements. Okay? And you can find the voltage on each element, find the current through each element, and then you can calculate the power on the circuit as a result. And usually, all the sums of the powers dissipated and given out by each of the elements have to add up to 0 by energy conservation. So one of the things you should know is that all powers would add up to 0. Okay? All powers would add up to 0. So this must be revision for you. But let me go to section 1.2, KVL and KCL. It stands for Kirchhoff voltage law and Kirchhoff current law. Okay, let me write it down. And Kirchhoff voltage law says something very simple. If you were to have a circuit, if you were to go around in a circle, the sums of the voltage drops on each element in this circle should add up to 0. Okay? One way to say KVL is that sum of voltage drops add up to 0. If you were to count it that way,